Hello students, welcome to the lecture on statistical process control and process capability, and after this lecture we will be able to learn the following objectives: explain control chart, discuss process capability, explain process capability analysis, describe control limits versus specification limits. Let's start with the introduction. Statistical process control is an analytical decision-making tool which allows to see when a process is working correctly and when it is not. Variation is present in any process. Deciding when the variation is natural and when it needs correction is the key to quality control. The concepts of statistical process control (SPC) were initially developed by Dr. Walter Shewhart of Bell Laboratories in the 1920s and were expanded upon by Dr. W. Edwards Deming, who introduced SPC to Japanese industry after WWII. After early successful adoption by Japanese firms, SPC has now been incorporated by organizations around the world as a primary tool to improve product quality by reducing process variation. Variations due to assignable causes of variation are present in most production processes. These causes of variability are also called special causes of variation. The sources of assignable variation can usually be identified, assigned to a specific cause, leading to their elimination. Chance variations. Random variations. The basic purpose of studying a sample is to estimate the value of a parameter, such as the average birth weight of a baby girl, in the broader population from which the sample was drawn. All studies are based on samples of people, and people vary, so different samples from the same population are likely to give different results purely by chance. Let us now discuss the definition of control chart, a set of methods for monitoring process characteristics over time called control charts, and places these tools in the wider perspective of quality improvement. Control charts are the basic tools of statistical process control. They are simple to construct and use and are very useful at lending to process improvement. According to W. Edwards Deming, Shewhart perceived that control limits must serve industry in action. A process, even in statistical control, wavers. Control limits can thus not be associated with any exact probability of looking for trouble, an assignable cause when there is none, nor with failure to look for trouble when an assignable cause does exist.
Hi, this is Chris Heffley with Bandit Software, and we're continuing our look at some of the newest features we've recently added to LeanKit Kanban. One of the features we're most excited about is the addition of statistical process control charts. A statistical process control chart is a way of measuring or a way of examining the stability of a process and a way of looking at the variability in that process. We use that to look at lead time and or cycle time and analyze the variability in that metric for our Kanban systems. So here's an example process control chart. I'm going to modify this a bit and change the start lane so that starting in either work queue or in process is valid. This finish lane is still done. We're going to restrict it to everything after January 1st and recalculate. And what we can see here is these green dots here are cycle time measurements. So each of these green dots represents an item that reached the done state and the cycle time for that item. So you can see we're obviously releasing things for this particular process in batches. So here's a batch here, another here, another here. The mean is obviously the average cycle time across the entire process, and the upper control limit is 3 standard deviations from the mean. Lower control limit is represented as well. So I can click on each one of these. If I start to look for the outliers and want to figure out what those are, I can get the card details for that and then jump directly to the card detail. This will open in a new window. Now say something changed around the 23rd of February, and I want to start recalculating our metric as of that date. So I can go in here and add a control point as of the 23rd of February, refresh the data, and the mean and upper control limit will be recalculated as of that date and shown on the graph. So the mean changes just a bit from 21 days up to 25 days, and the upper control limit changes a bit as things get a little less predictable. Let's add another one again as of, say, the 2nd of April and see what that does. Oh, by the way, April 2nd. So again, you can see you can slice and dice the statistics and recalculate on the fly to show, to analyze the stability of your process and the amount of variability in it. Another thing that's very useful in terms of providing an SLA for different types of work in your environment is to be able to analyze this kind of process control data based on class of service. So we'll take a look at the same chart by class of service. We'll reset the start lane again, and we'll pull it down to January 1st. And let's take a look just at the standard class of service, which should be most of our work. You can see that the mean is 23 days, almost 24 days, and the upper control limit is 95 days, so 3 standard deviations away. If I look then just at expedite work and see how that changes. Remember, we had 23 days and 95 days. Let's see how it changes just for expedite work. See, it gets a little bit shorter on the average, about 6 days faster. The mean is 19 days. The upper control limit is 77 days. We're very excited about this particular feature. We think it's one that will enable teams that are beginning to move towards maturity in their lean and Kanban systems to provide the kind of predictability, management of a mature process, and the kind of analysis, the deep, flexible analysis that will allow them to make very targeted improvements to their process and very confident predictions on the service level agreements that they can provide for different kinds of work in their Kanban system. Thank you very much, and stay tuned for even more screencasts on the newest features in LeanKit Kanban.
Comparison of univariate and multivariate control data. Control charts are used to routinely monitor quality. Depending on the number of process characteristics to be monitored, there are 2 basic types of control charts. The first, referred to as a univariate control chart, is a graphical display of one quality characteristic. The second, referred to as a multivariate control chart, is a graphical display of a statistic that summarizes or represents more than one quality characteristic. Characteristics of control charts. If a single quality characteristic has been measured or computed from a sample, the control chart shows the value of the quality characteristic versus the sample number or versus time. Why control charts work? The control limits as pictured in the graph might be 0.001 probability limits. If so, and if chance causes alone were present, the probability of a point falling the upper limit would be 1 out of 1,000, and similarly, a point falling the lower limit would be 1 out of 1,000. Types of control chart. We have 2 main types of control charts. One for variable data and the other for attribute data. Since now worldwide the current operating level is number of parts defective per million parts produced, apply described as ppm, control charts for attribute data has no meaning. Life beyond the mean and range chart. Statistical process control is based on a number of basic principles which apply to all processes, including batch and continuous processes of the type commonly found in the manufacture of bulk chemicals, pharmaceutical products, specialty chemicals, processed foods and metals. The principles apply also to all processes in service and public sectors and commercial activities, including forecasting, claim processing, and many financial transactions. One of these principles is that within any process variability is inevitable. Control charts for variables. There is no readily available means for correcting, adjusting, or taking action on it. If the observed difference is known to be due to a special cause, then a search for and a possible correction of this cause is sensible. Adjustments by instruments, computers, operators, instructions, etc. are often special causes of increased variation. In many industrial and commercial situations, data are available on a large scale. Dimensions of thousands of mechanical components, weights of millions of tablets, time, forecast, actual sales, etc. And there is no doubt about the applicability of conventional SPC techniques here. Several control chart techniques exist which make use of other measures. Our objectives for this part are to learn how to use control charts to monitor continuous data. We want to learn the assumptions behind the charts, their application, and their interpretation. Since statistical control for continuous data depends on both the mean and the variability, variables control charts are constructed to monitor each. The most commonly used chart to monitor the mean is called the chart. There are two commonly used charts used to monitor the variability, the R chart and the S chart. Procedure for using variables control charts. Determine the variable to monitor. At predetermined even intervals, take samples of size n. Usually n is equal to 4 or 5. The R chart. The R chart is used to monitor process variability when sample sizes are small, n is less than 10, or to simplify the calculations made by process operators. This chart is called the R chart because the statistic being plotted is the sample range. The S chart. The S chart is used to monitor process variability when sample sizes are large, n into 10, or when a computer is available to automate the calculations. This chart is called the S chart because the statistic being plotted is the sample standard deviation. The X bar chart. This chart is called the X bar chart because the statistic being plotted is the sample mean. The reason for taking a sample is because we are not always sure of the process distribution. By using the sample mean, we can invoke the central limit theorem to assume normality. Use of control charts. Control charts are used to investigate the variability of a process, and this is essential when accessing the capability of a process. Data are often plotted on a control chart in the hope that this may help to find the causes of problems. Charts are also used to monitor or control process performance. Charts for individual or run charts. The simplest variable chart which may be plotted is one for individual measurements. The individuals or run chart is often used with one at a time data, and the individual values, not means of samples, are plotted. The center line CL is usually placed at the center of the specification, the mean of past performance, frequency of sampling. Inspection involves measuring, examining, and testing products, process, and services against specified requirements to determine conformity. The use of inspection has been evident throughout the history of organized production. Effect of the sample size. The sample size has a major effect on the quality of statistical conclusions. This is reflected in the size of the confidence intervals for estimated distribution parameters such as mean and standard deviation. Some control chart patterns. Statistical process control charts have been widely used for many years to monitor the quality characteristics of a process. A process is considered out of control if a point falls outside the control limits or a series of points exhibit an unnatural pattern, also known as non-random variation. Analysis of unnatural patterns is an important aspect of control charting. Let us discuss process capability. A critical aspect of statistical quality control is evaluating the ability of a production process to meet or exceed present specifications. This is called process capability. A simple view of process control and process capability follows. Process control refers only to the voice of the process, looking at the process using an agreed performance measure to see whether the process forms a stable distribution over time. Process capability measures the goodness of a process, comparing the voice of the process with the voice of the customer. The voice of the customer here is the specification range, tolerance, and/or the nearest customer specification limit. Process performance requires that the standard deviation estimate come from the overall data set, simple sample. This means that there is no time component involved in long-term estimate of the standard deviation, hence all of the sources of variation are combined. Process capability requires that the standard deviation estimate come from subgroups of data, rational subgroups where the variation within them is considered homogeneous. This means that the variation over time will exist between subgroups, but that the variation is homogeneous within the subgroup. Process capability is also the ability of the combination of people, machine, methods, material, and measurements to produce a product that will consistently meet the design requirements or customer expectation. Process capability study is a specific and a systematic procedure that uses control charts to detect and eliminate the unnatural causes of variation until a state of statistical control is reached. When the study is completed, process capability measurements allows us to summarize process capability in terms of meaningful percentages and metrics. To predict the extent to which the process will be able to hold tolerance or customer requirements. Based on the law of probability, we can compute how often the process will meet the specification or the expectation of customer. We may learn that bringing process under statistical control requires fundamental changes, even redesigning and implementing a new process that eliminates the sources of variability now at work. It helps choose from among competing processes the most appropriate one for meeting customers' expectation. Knowing the capability of our processes, we can specify better the quality performance requirements for new machines, parts, and processes. Let us now talk about the process capability analysis. Capability analysis is a set of calculations used to assess whether a system is statistically able to meet a set of specifications or requirements. To complete the calculations, a set of data is required, usually generated by a control chart. However, data can be collected specifically for this purpose. Specifications or requirements are the numerical values within which the system is expected to operate, that is, the minimum and maximum acceptable values. Occasionally, there is only one limit, a maximum or minimum. Customers, engineers, or managers usually set specifications. Specifications are numerical requirements, goals, aims, or standards. It is important to remember that specifications are not the same as control limits. All methods of capability analysis require that the data is statistically stable with no special causes of variation present. To assess whether the data is statistically stable, a control chart should be completed. Capability analysis is summarized in indices. These indices show a system's ability to meet its numerical requirements.
How do we measure process capability, and how do we calculate the measures, and how can we make sure that we're doing it properly and understanding whether the process that we're working with is actually capable of delivering the type of result that we intend. So the result that we intend would typically be called our design specification. This is what we expect the product or the service to deliver. And as we can see here, it's shown by this bracket up here, showing this is our specification. We expect the average of our process to be here, and we expect to have no more defects than these two ranges. This is our lower control limit and our upper control limit up here. We can see a process here that's not capable of meeting specifications all the time because some values are going to fall way out here under the tail of this curve. Some are going to fall out here above the upper control limit. And in this case, we have the same type of design specification, but we have a process this time that is capable. We're going to see that the values that fall in this normal random distribution are going to fall within our design specification most of the time. Well, let's take a look at how a process that is in specification, that does meet the specification, in fact it meets it very well, we have plenty of room here. However, that design or that process itself can be off-center. It may fit within the boundaries, but we can see that the average is too high. In this case, we're going to get some values out here beyond the upper control limit that are going to fail or are going to be defects. So let's figure out a way to calculate using our historical data and our design specification whether our process is going to be capable of delivering the results that we expect. The primary measure is called a process capability index, or called CPK. And in this case we're going to take a look at X bar, which is the average of our sample means. So if we have multiple samples, each sample has a mean, we're going to average all of those sample means, and we end up with what's called X bar bar. And in this case we're going to look at the minimum, the lesser of these two, the upper and the lower control limits. The lower one would be our X bar bar, which is our average, minus our lower specification limit, divided by 3 sigma, our standard deviation. And our upper specification limit minus X bar bar divided by 3 sigma, or 3 standard deviations as well. Let's take a look at the math and how that would work. In this case we have a net weight or a specification on our product that's 9 ounces plus or minus a half ounce. We have historically found that the process mean is delivering us, or the average is delivering us 8.8 ounces. And the standard deviation is 12 tenths of an ounce, 12 hundredths of an ounce, 0.12. So in this case, we'll take X bar bar, which is our process mean of 8.8, subtract our lower specification limit, and divide that by 3 sigma. So we know that 8.8 is our average. 8.5, which is 9 minus our 0.5, gives us our first value. We'll divide that by 3 times sigma, which is our standard deviation, so that would be 0.36. So 8.8 minus 8.5 divided by 0.36. And our other value is 9.5 minus 8.8 divided by 3 times sigma again. Now what we want to do is take whichever one of these values is the least, is the one that we're going to work with. In this case, the lower value is 0.83. And a CPK that's less than 1 tells us that our process is not capable. Our process is not capable. So if you think about what we're doing here, is we are determining whether half of our value, which would be the middle, or our average, minus our upper or lower control limit, and we're using 3 in this case, which is each side of our distribution. In this case, we want to make sure that we're fitting in 3 standard deviations here and 3 standard deviations here. So we want to find out if the distance here in our specification matches up with the distance that we're going to find on this curve. So if that ends up being less than 1, we're going to have a situation like this, because we have this distance right here, is going to be less than the distance that we have right here. So that's going to be less than 1 from our process mean to this control limit is going to be less than 3 times sigma. So in that case, we have a process that's not capable because that leaves these guys out here. Some of our values are going to fall out beyond it. So let's take a look at what that means in terms of our process capability. As I've just said, a process that yields a CPK of less than 1 is not capable. If 1 is capable, it's capable at 3 sigma, which is what we just talked about. Since we're using the value 3 sigma as the denominator, and 3 sigma would indicate the distance using 3 sigma. In the case of this one, if this were 3 sigma as we measure from our design specification center out to the tail of our distribution, 3 sigma, it's going to be capable at 3 sigma. And if you follow the math, it would be capable at 4 sigma at 1.33, 5 sigma 1.67, and you simply double the 3 and you get its at a CPK of 2, we're going to be capable at 6 sigma.
Measures of process. Capability process. Capability indices CP, CPL, CPU and CPK are the 4 most common and timed tested measures of process capability. Process capability indices measure the degree to which process procedures output that meets the customer's specification. Process capability indices can be used effectively to summarize process capability information in a convenient unitless system. CP and CPK are quantitative expressions that personify the variability of process, its natural limits relative to its specification limits, customer requirements. Process capability index CP. Process capability index CP is a simple relative number comparing value of the required process variability, required tolerance interval to a natural process variability, natural tolerance interval. For measuring process given by expanded uncertainty U, capability index CP is calculated as CP is equal to 2U by 6 sigma is equal to U by 3 sigma, where S is a process standard deviation whenever requirements put on measurement process are given by tolerance interval T. Such interval must be defined first. Tolerance interval T is defined as the difference between the upper tolerance limit UTL and the lower tolerance limit LTL. That means T is equal to UTL minus LTL. Process capability index CPK. Capability index CPK reacts to deviation of the measurement process average mean X bar from check standard nominal value XO. Index is calculated as CPK is equal to U minus mod theta minus UKE upon 3 sigma, where UKE is the check standard uncertainty, mod theta is equal to XO minus X bar. Process capability index CPM. Practical experiences showed that demand for a low percentage of check standard measurements or measurements performed directly on products or processes falling outside the tolerance limit T is not satisfactory. Little information is obtained on spare measurements. Most interesting information is about the quality of individual measurements, that is, how far are measurements performed on check standard from the nominal value XO of the check standard or from tolerance limits respectively. CPM is equal to UTL minus LTL upon 6 K tau is equal to U upon 3 tau.
Capability, we're going to use a histogram. And the histogram simply says on the lower side, our customer wants a lower spec limit of X and an upper spec limit of Y. And here you can see we've got some buckets, and so how many widgets that we measured fell into this bucket. And here's our bell-shaped curve you can see. And there's a couple of metrics called CP and CPK which help us determine whether our process is capable. And anything that is a value of 1 or greater means we're capable, but it may not be as good as we would like. And then there's some other metrics like process and PP and PPK. These two help tell us a little bit if our process, these two, PP and PPK, should be close to CP and CPK unless there's a problem. So one of the things people get confused about in Six Sigma is sometimes they go, well, I want to set the control chart limits. No, you cannot set control chart limits, right? Those are set by your data. So control chart limits, the UCL and LCL, are calculated based on your data. Specification limits are set by your customers and used in histograms. So that's one of the more common confusions that people get into, so I just wanted to touch on it so that you're a little bit aware. Now in histograms, once you have a spec limit, you know, both spec limits, and you end up with a CP that's greater than 1 and CPK greater than 1, CP really measures, does that process fit between the spec limits, you know, or does it span over it? If it's less than 1, then you got some problem solving to do. All right? And CPK is really a measure of how centered is the process, because your customer probably wants you to be on the target line in between the spec limits, not, you know, skewed off to one side or the other, right? And so that's what we want to do, is find a way to adjust our process so that we increase CPK. Now, if CP and CPK are both greater than 1, your process is capable. However, most manufacturing customers require at least 1.33. And how does CP and CPK relate to sigma? Well, a CPK of 1 is 3 sigma, 1.33 is 4 sigma, 1.66 is 5 sigma, and a CP of 2 or greater is 6 sigma. So if you want to know where you are in the Six Sigma world, you know, this would be a way to capture that. So here's an example of some data, and this is the bursting strength of bottles. So let's say we're injection molding some bottles, and we have an upper spec limit and a lower spec limit of 346 and 200. Well, we could take this data with the QI macros, just select it, click on the chart wizard, and it'll start prompting us. And so I'm going to just put in our bursting strength of bottles here. Now, since there's no red points here, this means our process is stable. We can count on a bursting strength of 264 and varying between 220 and 308. Now what we want to do is come back to our data here, and let's use the upper spec limit and our lower spec limits here to draw a histogram. And our upper spec limit is 346 and the lower one's 200. It'll prompt us for bars, and this is bursting strength. Now here you can see we have some points outside of our lower spec and some points outside of our upper spec. Our CP and CPK here are 0.76 and 0.66. So we have a nice stable process, but it's not capable. So what we're going to have to do is find ways to squeeze this in to reduce the variability so that all of this stuff will fit in between our spec limits, and we can get our bursting strength back up to the level it's expected to be. Obviously a higher bursting strength is probably not such a problem, but a lower bursting strength might be, right? So this might cause some rework, failures, we don't know. So to reduce deviation, if we have a histogram that's got too much spread on it, too much variation, our CP is going to be less than 1. What we want to do is do some root cause analysis to figure out how to reduce the spread, to bring it inside, in between the upper and lower spec limits. If our CPK is less than 1, that means our process is off-center. And then all we have to do is move it onto center. So we want to center that process onto our target value. and continue to do this until we get to a CP of at least 1.33 and maybe 1.66 or 2.0. And that's how we use histograms to establish what our capability is and to find better and even more effective ways to meet customers' demands and achieve Six Sigma.
Control limits versus specification limits are defined as specifications are set by the customer. These are the wishes. Control limits are obtained by applying statistical rules on the data generated by the process. These are the reality. Process capability refers to the ability of a process to meet the specifications set by the customer or designer. Process capability is based on the performance of individual products or services, not the subgroup averages, against specifications set by the customer or designer, not the statistically computed control limits. Process capability is different from the state of process control, which is determined by control charts and based on the average performances of subgroups against statistical computed control limits. Difference between process capability and the state of process control. When measurement of an individual item does not meet specification, the item is called defective. When subgroup averages are compared with control limits and the comparison shows some unpredictable amount of variation, an out-of-control state is assumed. A process in statistical control does not necessarily follow specifications. A capable process is not necessarily in control. A process may be out of control and within specification or under control and out of specification. This is a crucial distinction that is frequently confused. Basically, specification limits have to do with the voice of the customer, while control limits have to do with the voice of the process. First off, what are specifications? Specifications define the allowable deviation from target or nominal. But to really understand what is going on, we have to define what we mean by allowable deviation, target, and nominal. The target is what we are trying to aim for. The nominal is what would be ideal. Target and nominal are frequently but not always the same. For example, if we are filling cereal boxes, our nominal is the net weight printed on the box. We do not want to give away free cereal. But on the other hand, we know variation is everywhere. And if we aim for that net weight, we are likely to get some that go the marked amount, which can lead to substantial fines. In that case, our process target is higher than nominal so that we do not have any boxes the net weight. Now in the end, let us summarize what we have learned in this lecture. Statistical process control is an analytical decision-making tool which allows to see when a process is working correctly and when it is not. Variation is present in any process. Deciding when the variation is natural and when it needs correction is the key to quality control. Capability analysis is a set of calculations used to assess whether a system is statistically able to meet a set of specifications or requirements. Process capability indices measure the degree to which process procedures output that meets the customer's specification. Processes which give data that fall into natural subgroups. Here, conventional mean and range charts are used for process monitoring. Control charts are the basic tools of statistical process control. They are simple to construct and use and are very useful at leading to process improvement. We know that all processes exhibit variation from the target, but how much variation we should tolerate before we adjust the process.